Alright, now welcome to the next exercise of the magnetic circuits. And this time we are going to do magnetic circuits with two MMF, two megamotive forces, which is basically two coils around the metal with their own current and their own separate number of turns. Okay, and this is the material, which is basically steel. So this metal is made out of steel, all of it. And this is the number of turns. We know this is 50 turns and we don't know the current I2, but we know this current I1 and we know this side's got 100 turns. We also know the length from this side to this side is 20 centimeters, and from this side to this side is 50 centimeters. It's quite a big one, but it's got 100 turns around this side and 50 turns around this side, so it has to be big. And they have the random numbers, that's why they are big, but anyway. So this one, the flux going through it is 3 times 10 to the minus 5, and this is the area of 0.15 meters square. And here is what's the requirements. I switch them around. I put drawing the magnetic circuit as A, and then as B I put find I2, which is the only unknown we don't have. Alright, so let's get started. Of course, our very first step is to mark the direction of the flux. And we are going to assume that the flux, actually we know that the flux will have the same direction, which is this one here. Okay, it doesn't really matter. It matters if there will be a split of flux, but in this circuit there is no split of flux, so basically it goes in one direction really. Oops. And also we have it as a fixed value, so it won't really change. We already know this is what it's supposed to be. The next step is to mark in the corners of the materials. So we call this one corner A, this one B, this one C, and this one D. And then the next important step before everything else is to calculate the length of the material or the metal. So L of steel will be equal with the length from point B and C, so L of B and C, plus the length from C and D, so L, C and D, plus the length from A and B, plus the length from A and B. No, that's A and D, sorry. A and D plus L, A and B. There you go. We know that two of them, C and D, it's equal with B and A, and that would be 50 centimeters. And that A and B and A and D, it's, there you go, this focus now, it's equal with B and C. A and D it's equal to with B and C, and that would be 20 centimeters. So let's rewrite it. So that will be equal with 50 plus, no wait, that's actually the 20. Let's write it properly. 20 plus, this is the 50 plus the 20 plus the 50, and that would be equal with 140 centimeters, or 140 centimeters, that would be 1.4 meters, wouldn't it? Yeah, and that will be a problem. Okay, actually, let's undo this. Let's say this one is 2 centimeters and this one is 5 centimeters. So there you go. Let's just get rid of them and make this one 14, and then this one will be 0.14 meters. Okay, why did I do that? Well, I realized this would be a ridiculous value. Like, I know we need 100 turns, but I don't think you'll ever make a meter long component, first of all, and second of all, it will mess up our calculations by a lot because it's such a big number. I don't even think you can put it on a graph for like the Teslas really, or like for the MMF will be so high, it will be higher than the input MMF, which will be quite ridiculous. But anyway, let's see. So let's say it's 0.14 meters in length. Okay, So L still it's equal to 0.14 meters. There you go. Now we know the length. And now we can go to our normal questions. So first is draw the magnetic circuit, and second is find I2. So let's draw the magnetic circuit. We have two coils and only one material. So that will be pretty self-explanatory. Since the coils and the MMF, it's a replacement of the voltage source. We'll put one here. We'll put one resistor here as for the material. Then we'll put another one here under squiggly F. There you go. Then this is the direction of the flux, and this is the reluctance of steel. There you go. So that will be 1 and this one will be 2. It's not very nice looking, but yeah, it should do. It should be fine. Anyway, now that we know, we have a vague idea how it should look like, let's start calculating it. So let's start by calculating the Tesla. So B will be equal with the flux divided by the area, and that one will be equal with 3 times 10 to the minus 5 divided by the area, which is given as 0.15 times 10 to the minus 3. There you go. And all of it should be equal with 0.2 Teslas. 0.2 Teslas. Alright, that's very nice because yeah, it will be easy to find this value since we'll use the more accurate, let's call it graph, which talking about, we need to use it now to actually find the magnetic force. So there you go. There's the graph. Just I have a few papers in here. There's the graph, and we need to find it for steel, and we know the value of Tesla's, it's 0.2, so it'd be this one here. So let's put the ruler on the 0.2, which is be around here, and then let's just do this. There you go. It should be pretty straight, and I'll say this one, it's about, let's say 20, 40, about 55, I guess. It's pretty much in the middle. So let's say it's 55. Okay, so H still, it's equal with, and that's like approximation equal, approximately equal to, that's why I put this thing on the top if you're curious. 5580 per meter. There you go. Area Teslas per meter. Okay, and then because as you can see here, these two are going in opposite direction, because this one is going in this direction and this one is going in this direction. They are conflicting from to each other. So the total MMF, the total motive force, will be the first one minus the second one, because they are opposite forces, and they will be equal with the MMF inside the metal, which is this one here. So it will be equal with H times L of the steel. Very nice and very simple. So we can do therefore, which is this one here, magnetic force 1 will be the number 1 of turns multiplied by the current 1, which we both know both of them, and then MMF 2 will be equal with the number of turns 2, which we know, multiplied by the current 2, which is the unknown, and that will be equal with, again, H times L. H times L. You can see, like, even like by knowing one material, the value of MMF inside one material, we can easily determine which one of these two is the predominant direction, So yeah, there you go. And let's write the values. Therefore, let me go kind of like zooming out. It's equal with number of turns, and 1 it's 100 multiplied by I1, it's 2 amps, minus 50 I2, because they are multiplied, it's equal with 55 multiplied by 0.14. There you go. and then that will be equal with 200 minus 50 I2 equal with, that would be 7.7. okay, therefore 50 I2 it's equal with 200 minus 7.7. you know this is a negative, we move it to this side, that will be a minus, but the minuses from both sides cancel each other, so it will be a positives. It's equal with 192.3. therefore I2 is equal with 192.3 divided by 50, and that will be 3.85 amps. So there will be a requirement of 3.85 amps for the current to go, for the flux to go in this direction. So yeah, and as you can see, the, oh no, it's in the reverse direction, isn't it? Yes, because this one it's higher. So we discovered now that it's actually in the reverse direction. It's not in this direction, it's in this direction. Okay. So yeah. Well, what if this value here was a negative? What if it was minus 3.85 or something like that? Well, that means that they probably would have gone in the same direction. You know, they want to be in opposite directions, but because they are in opposite directions in this formula, that means that this 3.85 is the predominant direction for the flux. So the flux will go in that way because there is simply more current going through it. I think that's how you calculate it. Oh no, wait, actually, yes, I think that's how you do it. We will look more into it more in the future, but if you are curious, that's the answer for I2. So no matter what direction the flux goes in, I2 will be equal to 3.85 either way. Okay, so that was an example with two MF sources inside the same the same material, and they'll generate their own magnetic forces. No, they'll generate the same magnetic force, and R, the material R, will be equal with both of them, you know, taken away from each other because they are going into the same direction. Yeah, in opposite directions, really. Okay, I'll pause here and we'll go to the next exercise. Alright, welcome to the next part of this video, which is magnetic circuits with an air gap in them. And yeah, I chose to do this one as well because calculating with an air gap, it's a bit different from them, but don't worry, this will go on very quickly because I've already given you the values that you need, but we'll still do the steps. And I also want to do, because as you can see in one of the papers here, which one is it? I think it's this one here. Yeah, there it is. We also have the formula to calculate air gaps. So let's get started. The material is simple, it's just steel again, and there's the air gap in here. And let's do our normal steps, which the first one will be the find the direction. The flux direction will be this one, to like spread out here, to like try to get over it. There you go. Then it will go like that here, and let's say it's going in this direction, it doesn't really matter. Okay, that was the first step. The next step is to, oh sorry, there you go. The next step is to mark the points. So this will be point, no, this side from here, this will be point A, this will be point B, this will be point C, this will be point D. Basically we mark out the like edges, this E and this is F. You know, there's a corner here, 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 and here, and there are two more here and here, because basically the air gap, it's a different material and it takes away from the length. It basically cuts the length away. All right, so let's see what we need to do. First is to draw the diagram, the circuit diagram, and then is to find the current. Well, drawing the circuit diagram, it's very simple. We can just do this. Well, just a second. Sorry about that. My sister is making noise. Okay, sorry for the pause. My sister was making noise. But anyway, okay, let's draw the circuit. Basically, the source, which is quickly F, which is this one here, it goes to the coil. No, it goes to the material. One of the materials is the cast steel, and the other material is the air. Because it does provide resistance, so we'll include it in as well. So steel, and this one will be for air. There you go, and this will be basically the diagram for it. That will present the direction. Alright, and now part B is to simply find current like usual. I asked to find the current again because this is the one that you really want to know because the easiest to change, and also because this one will go us through all the calculations. So like we'll go through all the formulas and how to do it. But anyway, let's get started. So A, no, not A, that's B. Okay, B, the Teslas, it's equal with flux divided by area again, and we have them here. The area is 3 times 10 to the minus 4, and the flux it's 1 times 10 to the minus 4. So you can already see what the Teslas will be equal to. So that will be minus 4. That one will be 3 times 10 minus 4, and that will be 0.33 Teslas. There you go. And now we need to find the magnetic force of the steel. And that'll be again very simple. We'll assume, and we'll again use this here. So this one is for the steel. We'll get our ruler. So 3.3, I think it should be, that's 2, and then 3.3 should be here, and let's say it's down there, and we are going to do it straight down because it's nicely, and that will be equal with 6. That's strange. In my notes I have 200, but this is nowhere close to 200, is it? No, that's actually more close to 60. Probably I measured for cast iron. No. Oh no, it's not steel sheet, it's cast steel. That's the problem. Sorry about that. Yeah, it's cast steel, the material, and cast steel is this line here. Sorry about that. The other one was cast sheet, and that's why I thought it was the same one. Yeah, but basically we just put it at this point, and yeah, we'll get 200. That's why I have 200 in my notes as well. All right. So that would be equal with 280 per meter. There you go. And now we need to calculate the magnetic force inside the air, which is Hg. And the formula for Hg, it's Bg over divided by Q permittivity of the air. Or we can rewrite it as Hg is equal with 796 multiplied by 10 to the power of 5 multiplied by Bg, the Tesla of air. And we know that the Tesla, it's 0.33. So Hg will be simply equal to 7.96 times 10 to the power of 5 multiplied by by B. That will be equal with 7.965 times 10 to the 5 multiplied by 0.33. And then as a result, Hg will be equal with 262.68 times 10 to the power of 3, 80 per meter. Area Teslas per meter, really, basically. All right, so now we know the magnetic force for both of them. And because we know the magnetic force for both of them, and also we know the length for both of them as well, because I give myself the length as well, so we can go quickly through it. We can easily calculate it. Calculate the MMF, the magnetomotive force. So MMF in MMF in steel, let's say steel, it's equal with H times L in steel, and that one will be equal with 200 times 200 times 10 to the power of minus 3, because it's in meters, there you go, which is equal with 4080. And then MMF for the air will be equal with H times L for air, and that one is equal with, and we know like for air there's 5 times 10 to the minus 3 meters because this is the air gap. Okay, so that would be 262.68 times 5 times 10 to the minus 3, and that one will be equal with 1.314 K AT, or we can write that as 1.314 times 10 to the 3 AT. It is actually quite really big, isn't it? Compared to the other one is 40, and this one is 1.314 K. So this one won't really make any difference. All the MF is going here through the air gap, and it makes sense because it's air. It will need more mega motive force, need more force to go through it, doesn't it? But anyway, so now we can calculate the total. So the total, oops, there you go, will be equal with the one for the cast steel plus the one for the air. So therefore, number of turns multiplied by the current will be equal with H times L for steel plus H times L for air, which is basically 40 plus 1.314 K, and that one would be equal with 1.32 K, rounded up really. Okay, so now we can rewrite it again as 100 multiplied by I, so basically it's 100I equal 1.32 K, and therefore, surprisingly enough, 1.32 K divided by 100, it requires only 13.2 amps to go through it, which is quite amazing. We can write down the values if you want. Actually, we can write it down as this one will be equal with 1.32K, and this one will be equal with 1.31K, and this one will be equal with 4080. That's 80 at the end of this one and 80 at the end of this one. You can write it like that as well if you want, if you want to like write inside the circuit. They didn't really mention because once you find the current, you don't really care about the values inside of it, and this one it's more of a representation of this magnetic circuit here. But anyway, so this was another exercise, quite easy as well. It's basically, instead of using a metal, you use air, and you calculate it in a similar way. The only difference is when you calculate the magnetic force that you have a set value to multiply by the Teslas, because air doesn't really increase as more than Teslas increases. Like this value stays constant, unlike this other two where they basically fluctuate depending how high the Tesla value is. But anyway, so this is how you calculate the gap of air inside of it, and hopefully you understand how to do this one as well now. And there will be two more. There will be one about a split flux, and there will be one more about how to calculate flux. All right, so yeah, hopefully you find this interesting, and hopefully you understand how to calculate it with the gap of air. In case you want to take all the MMF inside the gap of air, because it will always be quite big within it if it's reach a point of 1K 1.3K. And I'll pause here and we'll go to the next exercise. Okay, here is the next exercise, and this one is a parallel magnetic circuit. Why do I call it parallel? Well, you'll see in a second. First of all, let's mark in the flux direction, and you'll notice a difference here. You'll notice that there are two holes inside the material, and you go like, well, does that make a difference or does it not? And the answer is yes, it does make a difference, because the flux will get weaker as it goes through, because one flux direction will be this one here, like one loop, and then the other one will be here. And the metaphor loop is exactly what I mean, because the one flux will go in this direction like that, and then another flux will go in this direction like that. They are basically dependent from each other. Basically, the highest amount of flux will be in this side, this will be a medium amount of flux, and this will be the less amount of flux. Alright, as I was saying, so yeah, loops basically. So we can write these two rings as loops because the current is different in each direction. You can say this one will be loop 1, you can say this one will be loop 2. Again, like a mesh analysis, remember to always use the same direction for the loops, don't use different ones. And let's mark in the fluxes as well. So so this one will be flux T, this one will be, I wish I had bigger test space, this one will be flux 1, and this one will be flux 2, and there we go. Now we know the fluxes. Let's write down the points as well. So let's start with this corner. This one will be A, this one will be B, because the flux is spread, so let's mark it as a different length. This one will be C, this one will be D, this one will be E, and then this one will be F, the final one. There you go. Okay, so we find the lengths as well, and we know that as soon as it's done, because they fit the lengths that I've been giving you, so you don't need to like bother calculating. So we know that the length of B, C, D, E, this one, it's equal to the length of this one, which is 0.2 meters, and the length in this one, it's simply 0.05 meters, very similar to the previous one. Okay, so we don't need to calculate the lengths, that's fine. And oh, I forgot to give the area. So area would be equal with 6.10 minus 4 meters squared. I forgot to write down the area. We can't really calculate the area since we're going to need the width as well, but there's no way we know the width in this diagram, so yeah, we don't do the area. Anyway, first we are going to draw the circuit. So we know that it's only one source, which will be this squiggly F, and we know this is one current in here. There's one resistance, which is the material. There's another resistance, and there is another resistance here as well. Now you may wonder, like, Alex, why are there three resistances, three reductants? Yeah, reductances, because it's made out of only one material. However, there are three. Well, that's because of the flux, and yeah, the flux, it's affecting the reductance, doesn't it? Because this will be the reductance inside this square here, inside BAFE. So BAFE, this one will be the reductance in here of simply R of B and E, and this one again will be, all two of them will be B, C, D, E. That will be the reductance of B, C, D, E. And that's why they are different, because the flux will be different in each one of them. This one will have flux 1, this one will have the second flux, and this one will have the total flux. And why this one is the total flux while this one is flux 1 and flux 2? Well, similar like normal circuits, currents add together, so we can say like this will be a node, and then the total comes in, and then two other fluxes comes out. If you add in those two fluxes, it should be equal to the total flux, like in a normal circuit. Okay, so that's enough of drawing, to be honest, really, because yeah. So it's not necessarily always the material. If they are separate fluxes, you have to add in reductances as well, because they are not the same. That's why doing this type of circuit, of magnetic circuit, it's a lot easier in series compared to in parallel, and you'll see why. But anyway, let's get started. So we already did A, which is draw the circuit. Now B will ask us to find the flux, and that will include the total flux, and it will also include flux number 2, because we don't know the second flux either. We don't know the first one. We know the second flux, which is 2 times 10 to the minus 4. We don't know the first flux, and we don't know the total flux. So let's get started. So because we know the first flux, let's write here B. So because we know the second flux number 2, let's write it here as well. So that'll be 10 times 2 times 10 to the minus out of minus 4. We reverse WB, let's say. There you go. Well, we know that the B2 from flux will be flux 2 divided by the area, and that one will be equal with 2 times 10 to the minus 4 divided by 6 times 10 to the minus 4, and that will be equal with 0.33. all right, now let's go to the graph, because we know this one is 0.33 teslas, and we know the material being steel sheet. I don't want to like pronounce it wrong, to be honest, but anyway, let me start the flash on. There you go, so you can see it clear. Okay, so 0.33, and it was this line here. So let's see here, 0.33. There you go. It's this one. It's about around here, maybe. No, I think it's around here, 0.33. And to do down, and that would be 20, 40. That would be 60. So let's say it's 60. It doesn't have to be perfectly accurate. We can put any value really. So H2 for this one here, or we can also name it HBCDE. It's equal with 60 AT per meter. There you go. We don't need to put a bracket here. And then we are going to, as next step, apply ink Paris, I think it's like that, circular law at loop 2. Let's put in the loops as well. So this one will be loop 1, and this one will be loop 2, as seen in here. Okay, and what we know is that the how is it called, let me think actually with where I was going for this one. So this one is 0.2, and these two are equal, and because these two are equal and they use the same material, then they should be matching, shouldn't they? Yeah, so inside this loop it's like the voltage law, isn't it? So because we know the length of this one, and we also know the length for this one, and because they share the same MMF, we can write it as H times L bracket BE, it's minus H times L for the BCDE will be equal with 0. Why do we use this one and not use this one? Well, we already know the flux through it, and because we know the flux, we already determined the magnetic force, so we can use the magnetic force in this one here, because this one is like number 2 as well. There you go. So now we can simply replace the values and write them in here. So we know the how's it called, we don't know the magnetic force inside number 2, so that will be h multiplied by, but we know the length, and the length is 0.05 minus, and then h, the magnetic force, it's 60 for the second flux, that will be 60 multiplied by the length, which we know it's 0.2 from this one here. So multiply by 0.2, therefore 0.05 h, it's minus 60 times 0.2, what is that? That's 12, isn't it? 60 times 0.2, yeah, that's 12. Okay, minus 12, it's equal to 0. Therefore, when we can like simply write it as HBE, this line is for BE, it's equal, which is this line here. Again, I want to emphasize that we are applying basically Kirchhoff's voltage law, but it's named different. It's named Ampere circular law to this because they will share the same voltage. Like there, if you take away these two voltages, it'll be equal to 0. This is what I'm trying to get to. But anyway, HBE is equal with 12 divided by 0.05, and that will be equal with 240/80 per meter. A very nice number indeed. Okay, I hope you understand what I did here. It's like Kirchhoff's voltage law. Basically, the voltage of this one and the voltage of this one, they will be equal, and they will be equal to 0. But this formula, this method of doing it, it's of course for the magnetic circuits, not for normal analog circuits. All right, now let's keep going. So we can reverse it actually. So because we know the magnetic force, but we do not know the Tesla's, the density, we can inverse it. There you go. We can look at this piece of paper and look at the material, which is steel sheet, which is this line here, and we can use a ruler instead. And let's see, we'll have to use 240, so that will be 200 here, that will be 20, that will be 40, so it's like the second square. So there you go, 240. Need to make sure it's aligned. There you go, it's aligned as well, and it will be stopping at this point here, and that one will be 1.02, 2.04, 2.06. I think it's 2.08. So the answer will be around 1.08. So the flux density in this one will be, no, the Teslas in this one, in flux 1, will be equivalent to 1.08 Teslas. There you go. Therefore, now let's not put therefore, this one at the end. So flux 1 from the very original formula, basically we did, oh, I have it here also. Basically we did it the other way around. Instead of finding out the Teslas and determining the magnetic force H, we used the H to determine, no, we calculated H, and then we used the magnetic force H to determine the Teslas. And basically we'll just like, instead of writing this formula like this, we'll just rewrite it as flux 1 is equal to B1 multiplied by the area, and that one will be equal with 1.08 times 6 10 to the minus 4, and that will be equal with 6.48 times 10 to the minus 4 Webers. And there you go, we found now the flux 1, which will be 6.48 times 10 to the minus 4. And from here on out, it's really easy because like it's asking us to find the flux, and we will assume is the total flux, which we will simply do the following. The total flux, as you know the analysis, the total flux will be equal with flux 1 plus flux 2. So flux T is equal with flux 1 plus flux 2. Therefore, flux T is equal with 6.48 times 10 to the minus 4 plus 2 times 10 to the minus 4. And that will be equal with 8.48 times 10 to the minus 4. And that is the answer for part B, which was this one. Okay, I think we can fit in here part C as well, which is asking us to find the current. Which current is this one, I. We still don't know the current I, even though we found out the two separate fluxes. Well, let's see here. So let's write it here, C. And then what we know? Well, we know the total flux, and we also know the area. So now we can calculate the total Tesla. So P total is equal with flux total divided by the area. And that will be equal with 8 point, wait a second, let me check something. Yeah, I by mistake wrote the wrong values in my solution paper, so we'll have to calculate this on the fly. Okay, so that'll be 8.48 times 10 to the minus 4 divided by 6 times 10 to the minus 4. That will be equal with, so let's do this calculation quickly. 8.48 times 10 to the minus 4. There goes, you can see that as well. Divided by 6 times 10 to the minus 4. Alright, and that will be equal with 1.41. So about that, like 1.41. My little sister and brother, they have like friends over and they are screaming over each other. They are never going to be quiet. Anyway, so that's like the total BT. There you go. Let me like pause until they calm down, and then we'll keep going. Okay, hopefully you won't really hear that. You won't really hear that. I mean, they are kids. They don't always make noise anyway, and they are with their friends, so they'll like shout and run around and do stuff like that. But anyway, let's keep going. Let me focus. There you go. So next we need to find the value of H, because we know the Teslas, so we can easily find H by using the graph. So it's 1.41, so we are going to use the big graph now, this one, which has got higher values, and we are going to go around here. So 3.3, we should be at the half point, and it's about this point here, and that will be around 600. There you go, 600. So there are like 600 inside of it. So this would be 680 per meter, isn't it? Yeah, I think so. Okay, now we know the flux, the magnetic force, so we can calculate the MMFs. Now we can calculate this MMF in here, and we can calculate the MMF going through this resistance here. So, and also the MMF through the first loop, which will be through this resistance here as well. So let's keep going with then. So then this MMF is equal to MMF in loop 1, which is this one here, plus the MMF inside BE, which is this one here. Therefore, number of turns multiplied by the current will be equal with 600 times the length, which is 0.2, as we know here. Okay, plus 240 times the length, 0.05, because we already know the values inside this one. We already know that got the magnetic force is 240, and we already know the length because it's given here, 0.05. So we simply multiply them together, so that will be 50i equal with this one should be, let me check, 600 times 0.2, and that'll be equal with 120. So the first one would be 120 plus, and this one will be 12 because we already calculated the ones before. Therefore I will be equal with the total 152, oh no, 132, sorry about that, 132 divided by 50, and therefore I will be equal with 132 divided by 50, 2.64 amps. 2.64 amps. So to give us all of the values that we just calculated, the MMF should be supplied by 2.64 amps going through here. So we did find the flux and we find the current. Next we are going to need to find the permittivity for each section, which basically will be the permittivity through RBAFE, RBE, and RBCDE, which will be the three resistances really. We are going to need to find their permittivity. So this is not ready yet. I'll just change the page. I'll go to the next page, which it's here really. So let's quickly write here paramagnetic circuits. So parallel magnetic circuits. Okay, and we will go to the next exercise, which is finding the permittivity for each section, again for each one of these resistors. Now this will be very simple because we already know all the values that we need to know, so we'll just have to really write them in. So we'll start with flux 2, with this here, with RBCDE. So the permittivity of the material is equal with P2 divided by H2, which is the H in here, and that will be equal with 0.33 Teslas divided by 60, and that will be equal with 5.5 times 10 d minus 3. And now we can easily find the total one because we just applied the mole permittivity divided by the air permittivity, and that will be equal with 5.5 times 10 d minus 3 divided by, let's write it as 12.5, now let's write it as 4 times pi, it's easier, times 10 d minus 7, and that will give us a permittivity of 4375.5, and that is one of the permittivities. That is for R, B, C, D, E. There you go, or simply R2, let's say. Now let's go for the next one, which will be equal with B1 divided by H1 this time, which will be here for the BE. Okay, and then yeah, that's H1, so let's write it as BE, so there's no confusion between number 1 and the loop. Okay, so that one will be equal with 1.08 Teslas divided by 240, and that will simply give us 4.5 times 10 to the minus 3. And now let's calculate the total permittivity, and that will be equal with B1, no, that will be equal with U, let's put 1 into 0 as well, U1 divided by U0, which is the air again, and that will be 4.5 times 10 to the minus 3 divided by 4 pi times 10 to the minus 7, and that will be equal with 3580. That will be R1, or we can say RPE, depends how you want to write them or how do you want to see them. But anyway, now we will go to the last one, which will be this one, RBAF, which is this one here. So this one is number 1, B, C, D, E. B and E are its resistor 1, B, C, D, E it's resistor 2, and now we go to the total resistor, which is B, A, F, E. Doesn't really make sense, but let's just name it like that for now. So that will be BT divided by HT, and that one will be equal with what were the values for this one, because this one I got different. Yeah, that's 1.41 divided by, and then the permittivity was 600, wasn't it? Yeah, 600. And then that one will be equal with, so let me get the calculator out. I don't have the answer for this one. That one will be 2.35 times 10 to the minus 3. So 2.35 times 10 to the minus 3. And then that one will be the total for it. Yeah, the total change will be this one divided by the permittivity of the air. That will be equal with 2.35 times 10 to the minus 3 divided by 4 times pi times 10 to the minus 7. That will be equal with, so let me write it here, 2.35 times 10 to the minus 3, and then 4 times pi. No, wait, that will give me an error actually. I need to do pi times 4, so I can do this on times, oops, 10 to the minus 7. That will give me 1870.1, let's say. And that one will be RT, or we can name it BAFE. BAFE. And there we have it. We have the permittivity for all three of them. And remember, as in resistors, the higher the permittivity, as in like the higher the resistance, the lower the flux, meaning the lower the current. So the higher permittivity in these ones means that it's lower flux going through them. And that makes sense because the lowest flux value, it's in this one here, in flux number 2. And this one got the highest permittivity of 4375, while number 1 it's got the higher flux and it's got a lower permittivity of 3580, and then this one, the flux total, got the highest flux and it's got the lowest permittivity of 1870. So you can already see how permittivity affects the circuit, and you can already see how we can check our answers if they are correct or not. If let's say the total was less than 1 or 2, that means the answer was wrong, or if 1 was larger than 2, again the answer was wrong, because it wouldn't make sense, since the law of permittivity says that the strongest flux will be at the start, the middle flux will be at the middle of it, and the weakest one will be at the further of it. The further it goes from the source, the weaker the flux becomes. Because again, the flux prefers the shortest way and the way that has the less permittivity. Anyway, so this was how to calculate parallel magnetic circuits. And this is a bit more complicated than the series magnetic circuits, because you will have to take into account fluxes. And of course, I want to make it more complicated than this because it's already hard enough and we are not really in an advanced level. Maybe when we get to an advanced level of electronics, then yeah, we are going to like do it more complex ones. But one way that I think we can make it more complex is by adding another source in here, and then having to calculate this one as well, and also by changing some of the materials in some parts of it as well, and that will make it a lot harder to calculate, and it'll take even longer than it took us now. That's why I'm not doing a more complicated one, because this one will probably be a 2-part video, more than sure be a 2-part video. But don't worry, the next exercise, it's really short. It will be about calculating flux, and while knowing the current. So I will see you after this pause here. Alright, and welcome to the last one, which will be magnetic circuits to determine the flux. And this one, it's really easy, it's really short, so don't worry about it, the video will end soon. Anyway, okay, so what have we been given? Well, we know this is made out of cast iron, we know this has got 50 turns around it, and we also know this is got 5 milliamps. We know the length of this one is 0.5, and the area is 3 times 10 to the power of minus 4. So let's start in by doing the flux. Would simply, there you go, this is the flux. Marking the points, it's kind of useless since we already know the length, but we should do it anyway. B, C, and D. We already know the length, and we'll know the flux soon as well. Anyway, so first of all, it's draw the circuit. So that's our first task. So let's draw it. So there's the source F, then there's the resistor, which is basically just the cast iron, really, just the material. So R cast iron, because there's no splits of the flux, so you don't need to worry about that one. And that was basically drawing the circuit. And now let's calculate it. Actually, no, I have enough space, I'll just do it under it. So what asks is to find the flux. So N times I will give us the, how is it called, the MMF, and that will be equal with N iron multiplied by L iron, and we already know, oh no, not N, it's H, sorry, iron and times L iron, and we already know these two values. They are, let me write this, so that'll be 50 times 5, because that's the current, equal with, we do not know H yet, so H iron, but we know the length as being 0.5. Okay, and we can rearrange this one as H iron is equal with 50 times 5 times the current divided by 0.5, and then that one will be equal with 250 divided by 0.5, and that will be equal with 500 ATM, and area Teslas per meter. And we are going to use, like usual, the graph to determine the invert of it. Let's see here, do we have one that's tall enough? No, we don't really need one that's tall enough, do we? No, it's quite small if it's only 500, so let's use this one. 500 should be there, and it's cast iron, so 500 is here, and the cast iron, then we turn it around, and that one should be about 2.4, because it's passing 2 squares. Sorry, I don't think you saw that properly. There you go, 2.4, it's passing 2 squares. All right, it does have to be deadly precision, and it's quite hard to like align the ruler with only one hand, since I need to hold the phone with the other. So B, which is the Teslas of iron, will be equal with 0.24 T. And now we literally just worked our way backwards again, because B will be equal with the flux divided by the area. Therefore, because we know the area as well, flux, and we arrange this formula, will be equal with B times A, and that will be equal with 0.24 times 3 times 10 to the minus 4, and that will be equal to 0.72 times 10 to the minus 4 Webers, and that will be our answer. Basically the Teslas, which is 0.24, and the area, which has been given to us as 3 times 10 to the minus 4, and that's a different way how to find the flux. And you may want like, well, what do I need? Do I need to know this? Well, it's because all of these values here are measurable except the flux. You know the material it's made out of, which is iron, cast iron. We already know the length and the area, by using a ruler and measuring and calculating. And you already know how many turns are there. And if you made the circuit that provides the current, you already know the current as well. The only thing you can't really plug in something like a system and measure, at least a chip system and measure, is the flux really. And that's why it's important to also know how to calculate the flux if you only know the current really, because Either you want to determine the flux and know the value of the flux, or you want to know the value of the current. Anyway, and I hope, and this will be the end of this part 2 videos, and I hope you understand what I'm teaching you, and I hope you find it useful. Again, I think we'll run across this type of circuits in the future, because as I read, they have many applications like in radios or health systems or multiple systems, because it's very important to use them, and therefore it's very important to know how to calculate with them. All right, so this will be the videos for this session, and as I said, the next one will be about sine waves, sinusoidal waves. There'll be like sine wave, there will be triangle waves, star wave, square waves, and all types of waves, and we'll see how to calculate those. Okay, any last words about it? Well, just try to remember our steps, which is first to calculate the direction of the, let's actually write it down, why not? So remember these steps. Okay, first point, no, actually draw the flux flow. Then second is to mark corners of the materials / cap. Third is calculate the length for each. Fourth is to draw the circuit diagram. Alright, that's another thing to remember. 5 will be to calculate Tesla, which is the B. 6 is use the graph. For H, which is the magnetic force. If you remember these steps, you should find it easy solving magnetic circuits, really, because I noticed by doing them and doing various types of them that these are the main points, these are the main steps that you need to follow for each one of them. And remember that the graph plays this type of graph. If you want, search it on Google or download a picture of it. The way I did it, I have a manual for electrics, and I just took a picture of the manual and printed out. It's very useful, really, because as I said, you need to have a graph to know how to do it, to know how to calculate it. If the magnetic force is not given to you, and it probably won't be given to you, since if you know the magnetic force, then it is really easy to calculate the other values. But wait, I wrote 4 instead of 4, sorry about that. But anyway, this was the video basically, and I like, subscribe, comment, I guess. I don't know, I don't really get many views, and I know I won't get any right now because it's summer and I barely uploaded any videos, but hopefully over time I'll get some views, and hopefully I won't get any complaints either. I don't know, I guess I'll get better over time. And there it goes, my phone battery almost died, so my flash is off. Anyway, see you next video then. Bye guys.